We have discussed angles measured in degrees, but now we want to discuss angles measured in radians. First, let's talk about what 1 radian looks like. If I have an angle in standard position with its vertex at the center of a circle, our angle theta here would be called 1 radian. We define 1 radian by how much of the arc the angle intercepts. If our angle intercepts an arc length equal to the radius, so here's the radius of our circle, if the intercepted arc equals to the radius, then we call that 1 radian. In the past, we have discussed angles measured in degrees. In this section, we will look at angles measured in radians. Radian measure is defined by putting an angle at standard position at the center of the circle. So its vertex is at the center of the circle, and here we have our angle theta. Angle theta would be called here 1 radian. When we define radians, we are going to define it in terms of the arc length. And we will describe our angle theta as the arc length divided by the radius. So 1 radian will be that if the arc length that is intercepted by our angle, so here we have our arc length, if that arc length is equal to the radius, then we get 1 radian. So theta is equal to the arc length, which for this example is r, divided by the radius, and if the arc length is equal to the radius, then r divided by r would give us 1. So we would say that that is 1 radian. So now we define radians as the arc length divided by the radius, and that is how we will measure our angles in radians. So using this definition, what would 2 radians look like? 2 radians, an angle measured as 2 radians, would have our angle in standard position, and the arc length, for the arc length I will be able to lay 2 radii or 2 radiuses on the edge of our circle. So 1 radius, 2 radius. Since the arc length measures 2 radians, that would be 2r divided by r. Then theta is equal to what we call 2 radians. So it's the arc length divided by the radius. Here we have something that is half a radian. So here is my angle theta in standard position, and the radius is here. And if I was to lay the radius on the edge of my circle, we see that that would be too big, that the arc length intercepted by the angle is only this long here, and that is what we would say half a radius. So half a radius is my arc length divided by the radius. The r's would cancel, and we would say that we have an angle measured as half a radian. So half a radian. How would we describe then a complete rotation in terms of radians? So if our angle theta, if we have a complete rotation, if our angle theta is measured in radians, then we would have to define it as the arc length of a complete rotation, so the arc length of the entire circle divided by the radius. Well, the arc length of the entire circle is called the circumference of the circle, and the formula for the circumference of the circle is 2 times pi times r. And if I divide that by the radius, the r's cancel out, and I end up with 2 pi. So a complete rotation all the way around our circle would be 2 pi radians. Now this would be the exact value. If I wanted to find an approximate value for that, we know that pi is approximately 3.14. So 2 times 3.14, our approximate value would be 6.28 radians. And that represents a complete rotation all the way around our circle. So that would be our angle measured in radians. Now, what that means is that a complete rotation, if I look at the circle, I should be able to fit 6 radius on the edge of the circle. So 6 radiuses, or 6 radii. So 1 radius is here, so that would be 1 radian. I could fit in another radius, that would be 2 radians. Another radius, that would be 3 radians. We can see that we haven't done quite a complete half rotation here. We're almost to the half rotation, but not quite. We have to go a little bit more. So let's keep going. And I could fit another radius on there, so this would be called 4 radians. Here, this would measure 5 radians. And then another radius that would measure 6 radians. So we see that we need 6 radians laying end to end on the edge of my circle for a complete rotation, and then a little bit more. So all the way around would be 6.28 radians. Now in the past we have talked about degrees. 360 degrees used to represent a complete rotation in degrees, or it does represent a complete rotation in degrees, but now that we're measuring in terms of radians, 360 degrees is equivalent to 2 pi radians. So these really represent exactly the same thing, a complete rotation all the way around a circle. This is just 2 different ways of measuring that complete rotation, in terms of degrees and in terms of radians. Now, if I divide both of these sides by 2, I get 180 degrees is equivalent to pi radians. So half a rotation is actually equivalent to pi radians. And that makes sense because a half rotation was a little bit more than 3 radiuses, or a little bit more than 3 radians, and pi represents 3.14. So that makes a lot of sense. Now, if I wanted to divide that in half again, we would see that 90 degrees is equal to pi divided by 2. So where we used to have 90 degrees, now we will have pi over 2. And if you put pi divided by 2 in your calculator, you get approximately 1.57 radians. And that makes sense because we had 2 radiuses laid end to end, and 90 degrees came in between 1 and 2. So it looks about halfway between 1 and 2. So this is pi over 2, pi over 2. Every 90 degrees represents pi over 2. So 2 pi over 2, so if I have 2 of those, that would be pi. And then 3 pi over 2 would be what we now call, what used to be 270 degrees. And that now, as an approximation, is a little bit more than 4. It's in between 4 and 5. Looks like it's closer to the 5. So that's 4.71 radians if you put that into your calculator. And then as I go all the way around, of course, we get back to 2 pi. So we should be able to convert from degrees and radians. So go from degrees to radians and then back from radians to degrees. The equivalency here is that 180 degrees, half rotation in degrees, is equal to pi radians. That would be a half rotation in terms of radians. So if I were to take this little equivalency here and divide both sides by 180, we would see that 180 would cancel and give us 1. We would see that 1 degree would be equivalent to pi divided by 180 radians. And if I was going from 1 radian to degrees, if I wanted to convert from 1 radian to degrees, we can divide both sides by pi. So if I divide both sides of this equivalency by pi, pi divided by itself is 1, and then 1 radian would be equal to 180 degrees divided by pi. So if I take this equivalency and I solve for 1 degree or solve for 1 radian, then here are our equivalencies that we get. So we can actually use these equivalencies to convert from degrees to radians and then back from radians to degrees. To convert from degrees to radians, we will multiply by pi divided by 180. So whatever you want to convert to should go on the top. So if I want to convert 2 radians, then we would put pi radians on top divided by 180. And that'll convert us to radians. If I want to go from radians to degrees, we multiply by 180 divided by pi. And if I want to get to degrees, then I put degrees on top of my fraction. So let's do a couple of conversions here. Here we are asked to convert degrees Here we're asked to convert from degrees to radians. So 60 degrees converted to radians. It asks us to show the answer as a multiple of pi and also give its decimal approximation. So 60 degrees, let's make that look like a fraction, and we're going to multiply by pi over 180. So this is going to convert us to radians. So 180 degrees on the bottom and then pi on the top. So let's multiply across. When I multiply across, I get 60 pi divided by 180, and we can reduce our fractions. So 60 goes into 60 once, 60 goes into 183 times. So that would be pi divided by 3. This is what we would call a multiple of pi. So 60 degrees is equivalent to pi divided by 3. And this is our radian measure. If I would like to put this into my calculator and get an approximation, we would get about 1.05 radians. So 60 degrees is almost 1 radian. Negative 135 degrees, if I wanted to convert this to radian measure, we will multiply by pi divided by 180 degrees. That gives us negative 135 degrees times pi divided by 180 degrees. And if I were to look toward canceling common factors here, 45 times 3 would be 135. So let's factor that. So that would be 3 times 45 is 135, and then 180 is 4 times 45. And we see that they have a common factor, or they're both divisible by 45. So when I reduce this, I get negative 3 pi divided by 4. So this is our answer written as a multiple of pi. And if I would like to approximate that, I could put that into my calculator, and I would get negative 2.36 radians. So here we have the exact value, and then here we have the approximation. 325.7, I want to convert this degree measure to radian measure. So we will multiply by pi times 180, and when I do that, we get 325.7 times pi over 180, and if I leave it as a multiple of pi, it would look just like that. And if I would like to approximate that, I could put that into my calculator. I get approximately 5.68 radians. So here's our answer as a multiple of pi, and then here is our approximation. Radian measure is often given without any unit of measurement mentioned after it. So no specified unit of measurement. So if you have an angle measure that does not have a degree symbol and it doesn't have the word radians written after it, then we can assume that the angle is understood to be in radians. If I want to convert this radian measure to degrees, then I am going to multiply by 180 degrees on top divided by pi. And I am going to put that into my calculator. So I'm going to do 2.92 times 180 divided by pi, and the approximation, so this would be the exact. We're going to put that into our calculator, and the approximation will come out to be 167.3 degrees approximately. There's another way that we can actually do these, and this is a really useful, quick way to convert radians to degrees. Since we had defined that 180 degrees is equal to pi radians, then we can actually do a direct substitution. So if I see pi divided by 6 and I would like to convert to degrees, a really quick and easy way to do this is just to replace pi with 180 degrees. So pi would be the same as 180, and then pi divided by 6, I'm going to divide 180 by 6, and I get 30 degrees. And that's a really quick and easy way. Just substitute pi with 180 degrees, and that will get you to a quick and easy way to convert if it's written as a multiple of pi. So here we have 13 times pi divided by 3. So I can do a quick, easy conversion by doing 13 times 180 divided by 3. 3 goes into 180 60 times. So I'm really doing 13 times 60. And I put that into my calculator, I get 780 degrees. Another way that we could look at this as well is we could take pi divided by 3, and we could write this as 13 times pi divided by 3. And those would be exactly the same thing, exactly the same values, so because I do multiply across, we would get 13 pi divided by 3. But we know that 180 is the same thing as pi, so pi divided by 3 would be 180 divided by 3, which would be 60. So we could do 13 times 60, which would give us to the same answer as 780 degrees. Here we have our circle with all of our special angles that we talked about, 30 degrees, 45, 60, 90, and then the family of reference angle values given all the way around. So we're given all the degree measures that we have seen in the past and their radian measure equivalencies. So let's go back to that quick way that we talked about for converting from radians to degrees. So if you see pi over 6, pi is the same thing as 180. 180 divided by 6 is 30 degrees. Pi divided by 4. 180 divided by 4 would give you 45 degrees. And then 60 degrees would be pi over 3, and I could do that conversion very easily. 180 divided by 3, and that gives us 60 degrees. Here we have pi over 2, and that's the same thing as 90 degrees. So 180 divided by 2, and that gives us 90 degrees. As we go around our circle here, we're going to start to pick up the family of reference angles as we go through the rest of the quadrants. So here, this is our 60-degree reference angle family. And how would I know that this would represent 120? So we have 2 pi divided by 3. Now, a few minutes ago we talked about how we can actually separate this as 2 times pi divided by 3. And that's helpful because pi divided by 3 we know is 60 degrees. And 2 times 60 gets us to 120 degrees. So for our 45-degree family, here we have 3 pi divided by 4. Pi over 4 is the same thing as 45 degrees, and 3 times 45 is 135. 5 pi over 6, that would be 5 times pi over 6. Pi over 6 is 30 degrees, so that's 5 times 30 degrees, which gives us 150. Now, one thing that we will notice is that it's really easy to work with the reference angle families when we are written in radians. If it has a pi over 6 in it, that represents our reference angle of 30 degrees. So pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. All the pi over 6's basically are called the pi over 6 family, the reference angle family, and that's the same thing as 30 degrees. So pi over 6 we said was 30 degrees. This would be 150 degrees. That would be 7 times 30, so that would be 210 degrees, and then 11 times 30 degrees would be 330 degrees. So we're still working with that 30-degree reference angle family, but when we talk about radians, it's now called the pi over 6 reference angle family. And we have the same thing when it comes to 45-degree angles. So our reference angles for 45 degrees. Now we're going to call that, instead of the 45-degree angle family, the pi over 4 family. So the reference angle family for pi over 4, really easy to recognize because they all have pi over 4 in them. 45 degrees, 135 degrees, 5 times 45, we end up with 225, and then 7 times 45, we end up with 315. So a lot easier actually to recognize our reference angles in terms of radians. That's our pi over 4 family, and they all have pi over 4 in them. And 60 degrees, same thing. Pi over 3 is 60 degrees. 2 times 60 is 120. 4 times 60 would be 240. 5 times 60 would be 300 degrees. So our 60-degree reference angle family in terms of radians now would be called the pi over 3 reference angle family. For this example, we are asked to find tangent of 2 pi divided by 3. So tangent of 2 pi over 3, if we do our conversion, a quick conversion, what we're really looking for then is 2 times, we can think about that as pi over 3, that's 2 times 60. So what we're really looking for is tangent of 120 degrees. Now, if we think about pi over 3 as being equivalent to 60 degrees here, then what we're actually doing is we're putting our angle in standard position, and we're measuring off 2 segments of 60 degrees. So here's 60 degrees, that's pi divided by 3. We want 2 of these. So when I go 2 segments of 60 degrees, so here's another 60 degree segment, that would be 2 pi over 3's. So 2 pi over 3 radians can be found and graphed very easily by going 2 60-degree segments or 2 segments of pi over 3. And that's the same thing, of course, as 120 degrees. So we are in quadrant 2. Our reference angle, just by looking at it, we can tell that our reference angle is 2 pi, or our reference angle is pi over 3. Pi over 3. And 120 degrees, we also know, has a reference angle of 60 degrees. So if my reference angle is 60 degrees, and I'm in quadrant 2, then we know the sign and we know the number for tangent of 2 pi over 3. So the sign, well, we're in quadrant 2, tangent is negative, and the tangent value of 60 degrees, or pi over 3, is the square root of 3. So our answer would be negative square root of 3. In example B, we're asked to find secant of 7 pi over 4. So we want to measure off what our angle is, and that would be 7 times pi over 4. Pi over 4 is 45 degrees. So 7 times 45 degrees, that would be 315 degrees. Basically what we're saying is we are measuring off 7 segments of 45 degrees. So here would be 45 degrees, so we go one of those, and then second one of those will put us at 90 degrees, so here's another 45 degree segment, and another 45-degree segments. There's 3. Here's 4 45-degree segments. Go another one. Here's 5 45-degree segments. And then 6. And then here is 7 45-degree segments. Another way that we can think about this is in terms of radians. We could say that this is 1 pi over 4, 2 pi over 4s, 3 pi over 4s, 4 pi over 4s, 5 pi over 4s, 6 pi over 4s, and then here we hit 7 pi over 4s. There's a couple of different ways that we can count all the way around. But that's the same thing as 315 degrees. Now the quadrant that we're in is quadrant 4. Our reference angle is pi over 4, or 45 degrees. So if our reference angle is 45 degrees, secant of 45 degrees, let's pull that back up here, secant of 45 degrees would be square root of 2. So we have square root of 2, and since we're in quadrant 4, secant is positive. So our answer for secant of 7 pi over 4 would be positive square root of 2. So we find the quadrant that the angle is located in, and then we find the reference angle, and then we know the number and also the sign of our secant value. Now we are asked to find sine of negative 7 pi divided by 6. And just by looking at it this time, we should know that our reference angle is the pi over 6. That's that multiple of 7. So 7 pi over 6. We can tell because we have that pi over 6 that the reference angle would be pi over 6. And that's the same thing as 30 degrees. So a reference angle would be 30 degrees. What's the sine value at 30 degrees? Well, that would be 1/2. Now we don't know if we have positive or negative, and that depends upon what quadrant that we're located in. So let's look at negative 7 pi over 6, and let's see what quadrant that we're in. Now pi over 6, we're going to put our angle in standard position. We're going to go pi over 6 for 30 degree segments, and I need to go 7 of those in the clockwise direction. So here is a segment of 30 degrees. So there's one of those. Here's another segment of 30 degrees. There's 2 of those, 3 of those, 4, 5, 6, and 7. So 7 segments of 30 degrees going in this direction. That would be the same thing as going in the direction, let's say 30 degrees is pi over 6, so that would be minus pi over 6, minus 1 pi over 6, minus 2 pi over 6, minus 3 pi over 6, minus 4 pi over 6, minus 5 pi over 6, minus 6 pi over 6, minus 7 pi over 6s. So we can tell that we are located here in quadrant 2. What would be the degree measure equivalent to this? Well, pi over 6 we said was 30 degrees. So 7 pi over 6, negative 7 pi over 6 is equivalent to negative 210 degrees. And that all adds up and is consistent with what we know about negative 210 degrees. So is sine positive or negative in quadrant 2? The answer is positive. So the sine of negative 7 pi over 6 would be positive 1/2. Now we want to find cosine of 3 pi. So let's measure off and figure out where 3 pi is located. So remember that pi itself is a half rotation. So if I go all the way around 1 unit of pi, that is half a rotation. So there's 1 pi. 2 pi would be going all the way around the circle completely. So we have a full rotation. This says we have 3 pi's. So 1 pi, 2 pi, and then we keep going, another half rotation, and we hit 3 pi. So 3 pi is right here. Now we don't have a reference angle because it actually lays on the axis. So what was the point that we used before? Well, we used -1, 0. We use a point on the terminal side of what we call the quadrantal angle. So cosine, we're going to define that as, we said, x over r. So that would be -1 divided by r, which we said was 1. So -1 divided by 1 would be -1. So cosine of 3 pi is a quadrantal angle. We use the point that lays on the terminal side. We know our x, we know our y, and we know the r. X over r, we get our cosine value of 3 pi. We can also convert from radians to degrees here. So 3 times pi, of course that would be 3 times 180 degrees. And 3 times 180 degrees, and that would be equal to 540 degrees. So we can always convert to degrees and then find our angle, graph our angle, and then find the point on the terminal side and find cosine from that. Sine of -14 pi divided by 3. So we can convert to degrees if we want to. So that would be -14 times pi over 3. Pi over 3 would be 180 divided by 3, so that would be 60 degrees. And 14 times 60 degrees, that would give us 840 degrees, -840 degrees. So we can measure off that angle by working in terms of degrees. Or we could also count off 14 segments of 60. So let's practice with that idea. We're going in the counterclockwise direction, or sorry, the clockwise direction because we're negative. So we're going to start here at our initial side, and here is a 60-degree segment. So that's one of those. And here's 2 60-degree segments. And here's a third. And here would be a 4th, and a 5th, and here would be a 6th. So we go 1 of those, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So if I go 14 segments in that clockwise direction, this is where I would end up stopping. So we go 14 of those. Remember, that's the same thing as saying 14 pi over 3's. So all of these are pi over 3 segments. So this would be 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, 6 pi over 3, and so on. So we're right here in quadrant 3, and the reference angle, of course, is pi over 3. We could tell that just by looking, or 60 degrees. So what is the sine of 60 degrees? Well, that would be square root of 3 divided by 2, and sine is negative in quadrant 3. So sine of -14 pi divided by 3 will be negative square root of 3 divided by 2. So if we know the reference angle in the quadrant, then we know the trig function value.